Hi, everybody. Before we look at applications of polarity, we need to make a jump from being able to identify the molecular geometry, draw that, and then be able to identify whether the molecule is polar or non-polar. And that is going to answer a huge, huge question for us, okay? So I want you to open up your Cycle 4 notes here to this practice area. I had you keep this. Okay, and we're just going to go through for each and do the Lewis structure. Now, I'm going to assume that you can do the Lewis structure and you can get the shape. Okay, so the Lewis structure for this is like that: want minus half divided by 2. Okay, now I'm going to draw it. When they say shape, this means not identifying the shape, but drawing it in the correct shape. But we know that this is linear. Okay, so I'm going to draw it in the correct shape. And because both of these molecules are pulling in this direction and that direction, they have the same pull. Okay, there are no partial charges here, and this molecule then would be non-polar. Okay, meaning it's not being pulled in any specific direction. Okay, let's do CO2. Okay, so there's the Lewis structure for CO2. And we know that there are no lone pairs on the central atom, so the shape of CO2 is going to be linear. Okay. And we know with CO2 that there is a dipole arrow that is pulling in that direction. Okay. Because O pulls harder than C. And we know there's a dipole arrow pulling in that direction because O pulls harder than C in that direction. Both pulling it with an equal amount in both directions. There's no movement on this molecule. Okay, so we're not going to draw any partial charges, even though we know that those electrons are closer to that side and closer to that side, because this one cancels that one out. We're not going to draw any partial charges on the molecule. Remember, partial because there's not a full transfer, okay, because they're covalent. So this molecule also is nonpolar. Let's do the structure for water. We know if you end up with the Lewis structure for water, we have this. Okay, but these lone pairs we know push on the bond. So the shape of this molecule, the molecular geometry, is bent. Okay, now when we look at the dipole arrows, we know that O pulls harder than H. So we have an arrow going like this, and we have an arrow going like this. And what I'm going to do from now on is I'm going to be drawing these dipole arrows up here on the top left, just so you don't have to messy your molecule up here a little bit. Okay, so would these dipole arrows cancel? Okay, one this way, and it turns out they don't. You're going to have an overall molecular dipole going in that direction. They would cancel if they hit each other head to head. Okay, so that means that we will keep the partial charges. They do not cancel. The molecule has a partially negative here on this oxygen because it's pulling harder on those electrons, and a partially positive here on those hydrogens. And the overall molecule then is polar. So I want to take this opportunity to let you know that if the molecule is non-polar, you're going to have no partial charges. Non-polar, no partial charges. Okay? The dipoles cancel out. If the molecule is polar, they do not cancel out, and you keep the partial charges. Okay, so even in a molecule like this, where the simulation actually showed you these left over without the molecular dipole, I don't want you to show them. Okay, I only want you to show them when they're polar. When they're polar, partial charges. Non-polar, no partial charges. So let's do CCl4. This is going to be a tetrahedral molecule. We got your lone pair electrons on the outside of these chlorides. Okay, so when we draw it, tetrahedral is kind of tricky to draw. You can draw it this way if you'd like. That's totally fine. I mean, you can draw it down more in a tripod if you want, but so let's look at the dipoles here. So Cl is more to the right on the periodic table. So Cl pulls harder on the electrons. So we have a dipole going here, we have a dipole going here, we have a dipole going here, we have a dipole going here. So we have all these polar bonds. But is there a molecular dipole? No. These all cancel out. There is no molecular dipole, so the molecule is non-polar. That means we show no partial charges on the molecule. Okay, let's look here at CH2O. If we do the Lewis structure here like this, we end up with a trigonal planar molecule. Okay. Okay, so let's look at the dipoles here. O is more to the right on the periodic table than C. So there's a dipole going up here, there. And C is more to the right than H. And since everything's going in this direction, there's going to be absolutely no dipole at, they're not going to cancel at all. So we are going to get dipoles here. This is going to be partially negative, and this is going to be partially positive. I know that this is something I would normally focus on in class here, but this CH dipole is really tiny. So really the only dipole we're going to focus on here is the CO. So whenever you see C and H's, just go ahead and just ignore them. Don't even really worry about them. Pretend like they're not even there. Just completely ignore any dipole that would be there. But there is your polarity. Okay, so it is polar. Let's go ahead and do CH3OH. And when we do the Lewis structure for this, yeah. Okay, so here's your tetrahedral carbon. There's your bent carbon. Okay, I said just completely don't worry about the CH bonds at all. So when you look at the dipole arrows, they're happening right here. O is pulling harder than H in this direction, and O is pulling harder than C in this direction. Okay, so this molecule is not going to cancel out. They're not going to cancel because this is a bent region. O is pulling harder, so it's got the partial negative, partial positive, partial positive. Okay, and this molecule is polar. Let's look at NH3. There's the Lewis structure, and we're going to draw it according to the correct molecular geometry. It's pyramidal. Okay, so let's draw the dipole arrows. N pulls harder than H. It's more to the right on the periodic table. So we got an arrow here, we got an arrow here, and we got an arrow here. Okay. So these are not going to cancel out because these arrows are going slightly upwards. They're not hitting each other, but this one's pushing everything in that direction. So we got an overall molecular dipole there. The arrows are pointing towards nitrogen, so we make it partially positive. And because these charges do not cancel, the molecule is polar. Let's go ahead and do BH3. Remember, B is an exception. It only needs 6. Okay. So because there's no lone pair, it's going to stretch itself out into this trigonal planar look. B pulls harder on the electrons than H. It's got a higher electronegativity, so electrons are closer to it. But because there's no lone pair electron, all of these, this is a perfect 120-degree bond angle. So all of these end up actually canceling each other out. It's fully symmetrical. So the molecule here is non-polar. Notice non-polar, no partial charges shown. SO2. Okay. 1 minus half divided by 2. Now drawing it to the correct shape, we know that these lone pairs bend it. Okay. So it pushes it down. O is higher up on the periodic table than S. So O is going to pull harder. So if you're higher or more to the right, and if you mix that up, it doesn't really matter because you're going to end up with these actually not canceling out. See, I should have drawn them over here. not canceling out. They'd cancel out if they were this way, like CO2. So that means this is partially negative, partially positive, partially. So this molecule is polar. So in review, and I want you to listen really, really carefully to this, okay? If there are no dipole arrows or the dipole arrows cancel out in equal and opposite directions, like we saw with these molecules, you're going to call it non-polar, and there are going to be no partial charges left because they all cancel. Okay. If the molecule is asymmetrical, like we saw with H2O, where these dipole arrows don't cancel out and there's an overall molecular dipole, or right here, where these do not cancel out and there's an overall molecular dipole, or right here, the molecule is called polar. It's being pulled in a specific direction wherever those electrons are being gathered, and we show the partial charges. Okay, and then finally, if you have a CH bond anywhere, just ignore it. Doesn't really matter. Okay.